This video is on the quotient rule for derivatives. So we've previously seen that the derivative of the sum of two functions is equal to the sum of the derivatives, that we can take those derivatives separately for addition of two functions or subtraction of two functions. But we've seen that didn't work for products, that the derivative of f of x times g of x is in general not equal to the product of the derivatives, and we had a special product rule that arose from that. This time we are going to be investigating situations where there's quotients. In other words, is it generally the case that the derivative with respect to x of f of x divided by g of x is equal to the quotient of the derivatives is equal to f prime of x divided by g prime of x. So that is our question, and to investigate that, let's look at a particular example. Let's look at something that's easy to take the derivative of. Let's look at the derivative with respect to x of x cubed divided by x squared, and let's compute that in two ways. In the first way, we will first simplify that. So x cubed divided by x squared, that's simply x. And we know that the derivative of x is 1. And then we can also look at doing the derivative separately, and we don't know yet whether this will give us the same result. So if we look at the derivative with respect to x of the top of x cubed divided by the derivative with respect to x of the bottom of x squared, then that would be derivative of x cubed is 3x squared using the power rule. Derivative of x squared is 2x, also using the power rule. So then when we divide, that would give us 3 halves times x squared divided by x. That's just 1x remaining, 3 halves x. And are these two things equal? No. So our answer to the question above is no. So I'll now state the quotient rule for derivatives. We'll do an example and then we will prove that it is true. So for differentiable functions f of x and g of x, when g of x is not equal to 0, the derivative with respect to x of f of x divided by g of x is equal to g of x times f prime of x minus f of x times g prime of x, all divided by the bottom squared, all divided by g of x squared. So that's a bit of a mouthful, but I definitely want you to memorize it over the next week or so. You will be using it a lot. And a way a lot of people say it out loud is low d high minus high d low, all over the bottom squared. So that's just a way a lot of people sort of memorize it in their head. Low d high minus high d low, all over the bottom squared. And again, low g of x, low d high minus high d low, all over the bottom squared. So that's the way a lot of people kind of memorize it in their head. So let's see the quotient rule working with a really basic example, the one we saw above. So derivative with respect to x of x cubed over x squared. There's no need to use the quotient rule on this, but let's just verify that it matches with the derivative we found above. So derivative with respect to x of x cubed over x squared using the quotient rule, that's low, x squared, the bottom, d high, 3x squared, minus high, that's x cubed, d low, that's 2x, the derivative of the bottom, divided by the bottom squared. And so that's equal to, when we simplify, x squared times 3x squared, that's 3x to the fourth, minus x cubed times 2x, that's 2x to the fourth, all divided by x squared squared, that's x to the fourth. Continuing to simplify, that's equal to 3x squared minus 2x squared, that's 3x to the fourth minus 2x to the fourth, that's 1x to the fourth, divided by x to the fourth. And what is that equal to? That is equal to 1. And comparing that with the derivative with respect to x of instead simplifying what's in the inside, x cubed divided by x squared, if we instead did this by simplifying instead of the quotient rule, which I'd certainly recommend in general, simplify when you can before taking the derivative. That's derivative with respect to x of x, which is just 1. And yes, those two things match. Let's do the quotient rule with one more example where you actually need to use the quotient rule. Let's do the derivative with respect to x of, let's say, sine of x over x to the third. So the derivative with respect to x of sine x over x to the third, we need the quotient rule here. So that's low d high, derivative of sine x is cosine x, minus high, that's sine of x, d low, that's 3x squared, divided by the bottom squared, divided by x cubed to the second power. Let's simplify that a bit. So that's x cubed times cosine x minus 3x squared sine x, all divided by x to the sixth is what x cubed squared is equal to. You multiply, when you take the exponent of an exponent, you multiply those exponents together. And so that's, well, we could simplify a little bit more. We could make this x to the fourth times x squared and cancel out with that x squared and with most of that x cubed there. And so simplifying is going to give us x times cosine of x minus 3 sine x divided by x to the fourth. So that is our derivative of that function using the quotient rule. All right, now let's prove the quotient rule, which again says that for differentiable functions f of x and g of x, when g is non-zero, then the derivative with respect to x of f of x divided by g of x is equal to low d high minus high d low all over the bottom squared. So that's what the quotient rule says. Now let's prove it. So again, we're going to use the definition of the derivative to prove this. So proof, the derivative with respect to x of f of x divided by g of x is equal to the limit as h goes to 0 of g of x plus h. That's f of x plus h divided by g of x plus h minus f of x over g of x all divided by h. So that's the definition of the derivative applied to f of x over g of x. Now to simplify that, let's get a common denominator between those two fractions. So this is the limit as h goes to 0 of f of x plus h over g of x plus h minus f of x over g of x. And we're going to get a common denominator between those two fractions. So we'll multiply both of them by the denominator of the other. So multiply by g of x over g of x, multiply by g of x plus h over g of x plus h. And this is still all divided by h. So, okay, we've got the limit as h goes to 0 of, now it's all under one fraction, so f of x plus h times g of x, and then minus f of x times g of x plus h. I'm going to leave a little room there because we're going to add and subtract something in the middle. All divided by g of x plus h times g of x, all divided by h, but we can also just move that h into that denominator. So far we haven't changed anything, we've just rewritten the step above. And now we're going to add and subtract the same thing in the middle. So let's subtract g of x, f of x, and also add g of x, f of x. And so we've just added 0, which is okay to do. We mathematically have not changed that expression at all. And so let's again continue to simplify. That's equal to limit as h goes to 0 of, all right, so we've got g of x times each of those things. So this is g of x times f of x plus h minus f of x, all divided by g of x plus h times g of x times h. So that's sort of the first half of what we've got as a fraction, plus the limit as h goes to 0 of, now what do these two terms have in common? These two terms have an f of x in common, so f of x times, and then we've still got a g of x minus g of x plus h, all divided by same denominator, g of x plus h, g of x times h. All right, so what can we do with that? One thing we can do is separate out some of these limits. So that first one, that's equal to the limit as h goes to 0. Well, some of what I see there is the definition of the derivative of f of x. So I'm going to separate that out from the rest. So f of x plus h minus f of x, all divided by h, times the remainder of what's there. The remainder of what was there was the limit as h goes to 0 of g of x divided by g of x plus h times g of x, and we've got everything else out of there, plus the limit as h goes to 0. So what I see there is close to the definition of the derivative, because of I've got a negative g of x, or I've got g of x minus g of x plus h. Notice that's the opposite of the derivative. We normally have g of x plus h minus g of x divided by h. So I'm going to take a negative out front and switch the order of those two things. So g of x plus h minus g of x divided by h times the limit of h as h goes to 0 of everything that we've got out aside from that. We've still got an f of x left over and a g of x plus h left over, g of x left over. Okay, so I have just rewritten that into pieces. This is equal to, as we saw above, this is just the definition of f prime of x. So that's f prime of x, the derivative of f. And then we've got the limit as h goes to 0 of g of x, well, g of x does not change as h goes to 0, divided by g of x plus h. As h goes to 0, g of x plus h just goes to g of x, and so does g of x, minus the limit as h goes to 0 of this is just g prime of x, and then it's still multiplied by the limit as h goes to 0 of f of x, not changed as h goes to 0, over g of x plus h, g of x plus 0, g of x, times g of x. And finally, we can rewrite this as, okay, we've got g of x times f prime of x minus f of x times g prime of x, all divided by g of x squared, g of x times itself, g of x squared, and that is the quotient rule. That is the derivative with respect to x of f of x over g of x. We stated the quotient rule was this. It's low d high minus high d low all over the bottom squared.